Okay, this is Unit 3 of the DC theory. This is resistance. So let's take a look. Here's the objectives. Essentially what we've been talking about before is listing terms. We're going to be dealing with determining the values of resistors using resistor color codes. We'll be calculating total resistance in series, parallel, and series parallel circuits. And we'll be talking about the use of digital multimeter and how to take voltage readings. And also we'll be looking at resistance characteristics for fixed resistors, potentiometers, thermistors, RTDs, fuses, and light-dependent resistors. And this here is obviously just showing a picture of the different types of resistors. Big thing is you look from where the mouse is showing from the smaller resistors. These are like 1/8 of a watt, quarter of a watt, moving up towards a half a watt, and so on, up to these large. Here's 65 watt resistor, and that's obviously a very large resistor. And what's interesting is you can have the same resistive ohmic value, but it's the typical size. As the size gets bigger, that particular resistor can handle more of the heat dissipation that we talk about and when we will be talking about. Okay, so pretty much the size will determine how much you can dissipate in heat. Resistance, basic definition, opposes current flow. And here you see resistance and current are indirectly proportional. So if resistance goes up, current will go down. If current went up, then resistance went down. Resistance is measured in ohms. When you look, what will determine the resistive value, one of those things is the properties of the conducting material. So for example, if you look, copper has what's called a resistivity of 10.4. And you can look gold 14, silver 9.8. So on this whole curve, silver has the lowest resistivity, meaning it can conduct the best. Here you can see, look at carbon. Carbon, it says, see footnote B, carbon has 2,500 to 7,500 times the resistance of copper. And you're going to find that a number of these resistors, the composite material that it's made out of, is going to be a mixture of carbon. And you can see carbon has a high resistivity for the conducting of electricity. Let me click over on dielectric strength. This talks about some of the insulators that we'll use. And you can see vacuum is a good insulator. But these are dielectric strengths, meaning that even though these are good insulators, they will break down given enough high voltage. So here, this is kilovolts per inch. So if you look, air, 20 kV per inch, you'll start breaking down and you'll arc across the insulating material. So you can take rubber, 450 kilowatts per inch, you'll break through the rubber. All right, so this is just showing that insulators use what's called this dielectric strength. They're good materials, but they can break down, and then they'll literally conduct electricity. And in cases where we use it to insulate from the electricity, you can short circuit the ground, call trips, and so on. Anyway, that's the resistivity of resistors. Factors that affect the resistance. This is a good equation. So resistance is essentially equal to P is that resistivity we just showed earlier, times the length divided by the area. So as the length of the resistor goes up, the resistance will go up. If the cross-sectional area gets wider, then you're actually providing more cross-sectional area for electrons to flow. The resistance will go down. So again, if you increase the length, for example, in this resistor, resistor A, if the length is twice as long as resistor B, then because it's directly proportional, the resistance will be twice as, the resistance for A will be twice as much as the resistor for Bravo. Same thing here, if you increase the cross-sectional area, if you go from Bravo at 1 square centimeter to 2, then everything else being the same, the resistor that has twice the area will have half the resistance. Okay, so that's a good equation for remembering how resistance is calculated. Again, directly proportional to length, indirectly proportional to the area. Many resistors, notice it here, it says most conductors have a positive temperature coefficient. If you increase temperature, the resistance will go up. That's a positive temperature coefficient, and for those where temperature goes up, resistance drops, it's considered a negative temperature coefficient. We have fixed resistors, and you can see them here. A lot of them are carbon composite materials to determine the size of the resistor, or I should say the wattage of the resistor. Sorry, the resistance of the resistor. Increase in wattage is the physical size. This 2-watt resistor may have the same resistive value as the half-watt, but it can handle more current. Here you can see the symbol for the resistor. And with fixed resistors, you also have variable resistors. You can literally vary both manually and electronically vary the resistance of the resistor. These will be the two categories that we'll be using: fixed resistors and variable. We also have thermistors. As temperature increases or decreases, the resistance will change. RTD is very similar. You change the temperature and your resistance will change. A fuse, you're probably more familiar with fuses, all different sizes and shapes. We have a lot of these, these are like 2-inch fuses. The fused material, the metal that will actually overheat and break in half is inside of this. You may have seen some of these. This one down here, these are in cars. So you'll see these types of fuses. Bottom line is this metal will overheat, break, and break the connection for fuses. Photoresistors, again, similar to thermistors in that the light photons will see the surface of the resistor and the resistance will change. Okay, and again, the categories are shown with the asterisk: fixed and variable. This is a color code. This is a color code for a three-band resistor. So you see 3 bands and then 1 out here. That's for the tolerance. So here you can see the first digit, second digit, and the multiplier. So if you wanted a 100 ohm resistor, you would be brown, black times 100, which is red. So a brown, black, red would be a 100 ohm resistor. And as you can see here, if you had a gold band out here, the tolerance is 5%. So in that particular case, it would be 100 ohm plus or minus 5%. So it can go anywhere from 95 to 105 would be an acceptable resistor given those color codes. Remember, when they're making these resistors, as you move from silver to gold down all the way to the 1% tolerances, you'll actually spend more money buying those resistors because the tolerances are much tighter. The acceptance testing and so on for the resistor would literally cost you more money. But with you also have a like this one showing a 5-band, three digits, a multiplier, and the tolerance. Okay, same kind of, it reads pretty much the same way. First band, like in this one, if this is red, say it's red, orange, purple, and black, you'd be red, orange, so you'd have band 1 would be 2, it'd be 3, 7 for the third, so 2, 3, 7, and a multiplier of 1, so 237 ohm with a tolerance of, let's call this one, this brown color, even though it looks a little somewhat violet, is 1%. Okay, 237, 1%. And then we did a little exercise that calculated by looking at the colors what the values are. And sometimes you need a magnifying glass to help you determine these colors. But when you're using them every day, for those that use these colored coded resistors, they get used to what they are and they could easily pull them out of a bin. For us that don't use it that often, it takes a little bit of time, and of course to verify that you read the colors right is you test it with an ohm meter. And here you can see again the ratings As you physically go up in size, it'll handle the higher power rating. Resistors in series, you literally add them up. So in this particular circuit, 100 ohm and 200 ohm would equal 300 ohm. Again, you would add them up, 176 ohms. Doesn't matter how many you have in series, you just literally add them up, 565. In parallel, remember you're giving twice the cross-sectional area, so anytime you see resistors in parallel, you know that the total resistance will be less than the smallest one in parallel. So in this particular case, you know it's going to be less than 10. Turns out a good thumb rule is if you have the same resistors in parallel, you're going to be doubling. Like in this case, you'll be doubling the cross-sectional area, so your resistance will go up, or it'll drop by a factor of 2. So you take the number, 10 ohm, you 2 of them, divide by 2, and you get 5 ohm. So here you have 3. Remember, you're going to drop this by a factor of 3, so you take 6K divided by 3 will give you 2K ohm resistor. Again, now your cross-sectional areas are changing. They're not a direct, factor of, 10 or 2. This one you use what's called, when you have two resistors that are different values, you use what's called the product over the sum. So you would take the product, which is 200, divided by the sum, which is 30, and you would get 6.67 ohms. Notice, it's always going to be less than the smallest one, so you know it's going to be less than 10. And you can also use the reciprocal, 1 over R1, R2, R3, and so on. And you get the same value if you plug it in this way instead of product over the sum. Sometimes product over the sum is easier, but certainly in this particular case. But you can use the reciprocal, especially when you have multiple. When you look at that series parallel, you always work away from the source. So you deal with this parallel first. So you would do product over the sum with 200 ohm and 300 ohm, and then that effective resistance would be in series with the 100 and the 300. So you do the product over the sum. That'll give you 120 ohms. Notice 120 ohms less than the smallest one, 200. So then it would be 100, 120, 300 will give you the 520 ohms that the source would see. So the total resistance, once you evaluate this parallel branch, is 520 ohms. And we did a desktop experiment that focused its attention on calculating the series and parallel resistance. And this one again, when you're looking at how to use a multimeter on ohms, you definitely want to make sure in ohms that your circuit is de-energized. So this circuit would be okay. Switch is open. This one is not good. You can damage your multimeter. And this one too, sometimes it's not so easy to determine. But here, if you take it all the way back, you have a power supply, and you would have voltage across these resistors. That would not be a good connection. But this one is okay. And then we did a summary, and that was the end of the resistance module.